Hi, my name is KRISTA Schoonover, and I'm a rising senior at Case Western Reserve University, double majoring in mathematics and chemistry. Today, I will be discussing the competition between deprotonation and nucleophilic addition, providing computational insight into Silyl ketenes as molecular building blocks. I would like to thank my mentors and collaborators, Dr. Emily Pencer and Dr. Daniel Lembrecht, with whom I've been working for the past 2 summers. I would also like to thank PhD candidates Sarah Mitchell and Amanda Doomey, who have been very helpful this summer and last summer, providing data for the paper and helping me in a number of ways. This project is funded by the NSF, and I am proud to be part of the online research experience for undergraduates provided by Texas A&M University. So, Silyl ketenes present an entirely new class of polymer backbones, which is very exciting because most of the current polymer research explores methods to improve or adjust known polymer backbones, whereas we are pioneering entirely new polymers utilizing Silyl ketenes. The ketene itself is a carbon double bonded to a carbon double bonded to an oxygen. This is a very reactive molecule. And the addition of a silicon atom with 3 carbon substituents stabilizes it, making it ideal for polymerization studies. Very brief background on polymers. You join individual molecules called monomers, all the same, join them together into one extended chain that's called a polymer. The process is called polymerization. We are investigating anionic polymerization, where a negatively charged molecule called a nucleophile reacts with the ketene monomer, and thus initiating the polymerization. The polymer can then propagate by either the carbon or the oxygen atom, attacking the next monomer unit at the central carbon to form one of these 3 structures, with this being formed by carbon propagation, oxygen propagation, or alternating carbon-oxygen propagation. Each polymer backbone comes with its own special properties. This molecule is popular in developing nanostructures, which have a plethora of applications, including microchips and drug delivery systems. Either of these molecules can easily degrade with water and some small amount of acid or base, and thus would be helpful in eliminating or reducing plastic waste. Now I'll give a brief overview on the computational methods I've used. First, there's Avogadro, the molecular visualization software. You can build and view molecules and perform a few simple calculations, and it's very helpful in determining the shapes of molecules and making nice graphics for presentations or papers. Additionally, running geometry optimizations are the bread and butter of a computational chemist. You input a starting geometry and it finds the most stable configuration of the atoms. It outputs the molecular energy and partial atomic charges. From that, you can calculate reaction energies by taking the difference between the product and reactant energies. This provides the thermodynamic data for the reaction. You can also calculate a transition state search, where you input a product and reactant geometry and it finds the pathway between them. It outputs the geometries and energy of the pathway, and from this you can calculate activation barriers, and it also provides kinetic data. Before we go on, I would like to outline the motivation for my work specifically. Broadly, we are seeking to understand the reaction of Silyl ketene with a nucleophile. The nucleophile can either deprotonate the ketene, that is, remove this hydrogen and form this product, or add to the ketene and form the nucleophilic addition product, as I talked about previously. This product can easily access either carbon or oxygen propagation and seems to be less likely to form small molecules, more likely to polymerize. So I'll frame the talk around nucleophilic addition product being the desired outcome. Although really we do just want to have fast selective reaction with only one product and fully consume the ketene. So we would like to predict computationally which nucleophiles dictate which outcome, how quickly they react, whether they're fully consumed, and what other factors influence this. The direct motivation for this work comes from an experimental reaction of 4 nucleophiles with TBDPS ketene. All of them reacted differently. The reaction took anywhere from seconds to a couple hours with a different array of products and not always fully consuming the nucleophile. So we would like to be able to better understand and predict which nucleophiles will form what product and how quickly they will react. First, we calculated reaction energies to understand the thermodynamic properties of the reaction. A more negative reaction energy means the product is more stable, more thermodynamically favorable. We tested many systems, and the nucleophilic addition product is always more stable than deprotonation, making it the thermodynamically favored product. Since we observed a mixture of products in the lab, we hypothesized that some combination of a positive or unstable deprotonation energy, a very stable nucleophilic addition product, and a large difference between the two, as represented by the green bars, makes the nucleophilic addition the more likely outcome. So I collected a lot of thermodynamic data last summer, and here report on the new findings, which expand the scope of last summer's exploration. First, I looked into adding electron donating, methoxy, or electron withdrawing chlorine or nitro substituents to an array of nucleophiles, and here report on the results for phenolates. And the results are pretty much the same in all molecules that I tested. In general, the more electron withdrawing the substituent, the more unstable the products, and since the deprotonation reaction is more strongly affected, it results in an overall increase in preference for nucleophilic addition, represented by stronger green bars. In comparison, the electron withdrawing substituents had negligible effect or slightly decreased the preference for nucleophilic addition, so it seems that adding electron withdrawing substituents is more favorable for tuning the reaction outcome. I also looked at different Silyl substituents, that is, changing the carbon groups on the silicon atom. All products decreased, that is, became more stable as the size of the Silyl group increased, and as conjugated systems were introduced, that is, double bonded systems. Interestingly, the preference for nucleophilic addition stays consistent for all molecules, except it increases for TBDPS, likely due to some combination of steric and electronic effects. New this summer, I started paying close attention to the orientation of the molecules and ran many different conformation searches, looking at different attacking atoms, as well as different orientations of the nucleophile to the ketene. Shown here, we have the same nucleophile attacking with the oxygen or carbon atom and having very different geometries. The energy difference can be as large as 20 kilocalories per mole, which is very large. Some of these reaction energies are only 20 kilocalories per mole, so that could double the reaction energy. So the result of these searches is to have more confidence in our data that the most stable geometries are in fact being reported. Takeaways: nucleophilic addition product is thermodynamically favored, electron withdrawing substituents increase preference for nucleophilic addition, and the conformation matters. As I mentioned, we also ran transition state searches to understand reaction kinetics. Here I have plotted a sketch of the reaction pathway. Clearly, the nucleophilic addition reaction barrier is much larger than the deprotonation reaction barrier. I was not able to get data normally through 4-terbutanol, but my mentor found some data that the nucleophilic addition product is the reaction barrier is much higher than the activation barrier for deprotonation. In fact, there is a very negligible barrier for deprotonation reaction. So takeaways from the kinetic study: they're very difficult, time-consuming, finicky calculations to run. However, we were able to find that deprotonation is kinetically favored, the activation barrier increases with electron withdrawing character, and high pKAH, which is a characteristic of terbutanol, has negligible deprotonation barrier and a very large nucleophilic addition barrier. So key takeaways from this work: for all nucleophiles, the nucleophilic addition product is thermodynamically favored, and the deprotonation product is kinetically favored. Increased steric hindrance stabilizes both products, although it generally increases preference for nucleophilic addition. And the increased electron withdrawing substituents on nucleophiles increases the preference for nucleophilic addition. All that is left to do is to finish up some confirmation searches, a few remaining transition state searches, and some other miscellaneous data from different contributors. Finish up the paper, submit it. We hope to have that done by August, the end of August. And then we will continue working on different areas of siloketene research. With that, thank you all for watching. If this were live, I would definitely ask for questions, but as it is not, I hope you all enjoyed learning about siloketene reactivity. Please feel free to reach out to me with any questions at this email or post any comments. Thank you very much.